Hi, so our intent here is to go through the vocabulary for open channel flow very quickly. Basically, we're going to use this as a primer that we can go back to and print things as we move through the topic. So just looking at this, generally open channel flow can be subdivided into steady and unsteady flow, with unsteady flow being things that are changing with time, and steady is the thing that we're going to focus on. Uniform flows, where if we go upstream and downstream, there's very little change. So you need a long distance for that. So it's not very interesting. So this non-uniform flow is the area that we're going to focus on. Within non-uniform flow, there's gradually varied flow and rapidly varied flow. So gradually varied flow has one set of techniques to solve for, and then rapidly varied flow has the other. And then that can be subdivided further within gradually varied flow to downstream controls or upstream controls. We're going to go through that right now. So for the uniform flow, I guess you could say boring part, and it's going to be a baseline. We're going to call that normal depth often, and basically it's something like terminal velocity. So the water is moving downhill, and so it's burning off energy due to friction, but it's also gaining energy because it's moving downhill. There's a slope to the channel, and so basically if the water is moving too slow, it will accelerate until friction matches the amount of energy that it's gaining, sort of like a roller coaster or someone jumping out of a plane. They reach something like terminal velocity. So the Manning equation is the equation that describes that velocity. And so this person did a bunch of tests and came up with a coefficient that describes the roughness, Manning's roughness coefficient. And he needed some other things to solve the problem. One was the hydraulic radius, and the other was bottom slope. So the hydraulic radius is the area of flow divided by the wetted perimeter. So if you can imagine, we're going to do most of our calculations in a trapezoidal channel. And so if we have a channel that looks like this, this section's the area, and this section is a length that we would describe as the wetted perimeter. So it ends up being a unit of length. And then we need the bottom slope of the channel. We're also going to need to use the energy equation. So the idea here is that energy is going to be conserved. And so to do that, normally we would start with Bernoulli. And so we would say that the Bernoulli sum at one point is equal to the Bernoulli sum at the second point plus the head losses. And you've probably done that kind of thing with pipe flow. One thing of note, these are all expressed in units of head. And instead of using P1 over gamma, which would be the pressure head, what we're going to do is we're just going to say that that's the depth of the water. So that's great, and that works. You can do all these problems that way. But one of the things that we're going to try and do to simplify things is we're just going to say, hey, I'm not really that interested in elevation in general. Basically, I want to be able to get rid of that. So we'll get rid of both of these elevations, and we'll just say that we're going to take that into account somewhere else. Also, we're going to say that the friction loss isn't relevant, and basically it's going to be negligible. What we're trying to use this method for is rapidly varied flow. Maybe there's a down step or an up step, or the channel contracts really quickly. We can use this method. We can say the energy upstream is equal to the energy downstream and solve the problem. So to do that, we're going to use this thing called specific energy. And basically what that is it's taken out the elevation head, and it's taken out the head losses. And so we get something that looks like this. Now, if we take that equation, E is equal to the pressure head plus the velocity head, and we plot that out for a channel of a fixed geometry, we get a curve that looks like this one. So what you can see is that at relatively shallow depths, we've got a relatively small amount of pressure head and a relatively large amount of velocity head. That would be this point. Conversely, for a deep part of the channel, we would have a lot of pressure head and relatively little velocity head, and that's very intuitive. And so this shape is going to be one of the things that we'll go back to over and over again, because it will allow us to move from point to point. Now there's some other things that can happen. So for example, so this first figure, is for a fixed channel with a constant flow rate. If we had a fixed channel with varying flow rates, we would get a curve that sort of moves farther and farther to the right as we get more flow rate. So another way that you can get that same sort of a shape is if we had a channel that was getting narrower and narrower with a fixed flow rate. So for example, if we had a fixed flow rate and our channel got narrower, maybe it would start like this, and then the next time it would be a little bit less. Okay. Another thing that we need to be able to talk about is the Froude number, and the Froude number is a dimensionless unit. It's just the ratio of the velocity in the channel to the velocity of a surface wave. And so the equation for the velocity of a surface wave is the square root of gy, where g is acceleration and y is depth of water. So if the velocity in the channel is the same as the velocity of a wave, then we can say that the channel is at critical depth, or that a wave would kind of be trapped. And so what often happens is you'll see standing waves form. Now, if we had a Froude number that was greater than 1, then that would be considered supercritical. And what that means is that a wave couldn't travel upstream because the velocity in the channel is faster than the velocity of a wave. So that means that whatever's going on downstream can't affect what's going on upstream. So that means the upstream must control. Now, alternatively, if the Froude number is less than 1, that'd be subcritical. And in that case, it's your typical like inundation curve, the kind of flooding that we would expect. And that's because a wave can travel upstream. So specific force or conservation of momentum is going to be pretty easy to use, but we're going to start it off with something that's a little bit scary. So we're going to talk about impulse momentum. This is the idea of a jet of water striking a plate or being changed directions, and we can calculate the forces from that jet of water. So we're going to use that for hydraulic jumps. So to be able to do that, let's break out the sum of forces for a specific object. So we're going to say it's a hydraulic jump. So we're interested in a hydraulic jump. So here's the inflow water, and then there's sort of this swirling effect. And this is now our free body diagram for the sum of forces that we're going to use. So let's try that. So we've got a section 1, a section 2, and let's say that we've even got like a disturbance here. And so there's going to be a force from that disturbance, and there's going to be a hydrostatic force on either side. And so we can write that out as and then I'm also going to separate out, since this here is the mass flow rate, this is also the mass flow rate, and for our problems those two are going to be the same on the in and the out. So let's separate those out. So there's sort of the start of our derivation. So let's break that down a little bit more. If we look at hydrostatic pressure, that's just the pressure times the area. And so the pressure is the unit weight of the water times the centroid of that area. So what we can then say is Okay, so the next thing that we're going to do is rearrange this thing and put all the things that have 1 or 2 together. So here's some 1s, there's a 1, we're going to put those together, and then we're going to put the 2s together. So these things and that thing are going to be grouped together. And at the same time, we're going to run through this calculation where we divide by gamma. And so if we look at density, so density divided by the unit weight, is really just the density divided by the density times gravity. So it's going to be 1 over g if we take rho over gamma. So that what that does is it gets the density out. Nobody uses slugs, and so that's kind of what the goal is there. So if we rearrange that and we do that division, we end up with okay, so if we just do that simplification, rho over gamma turns into g, 1 over g. Then we get the other thing that we're going to do is we're going to get rid of q and v. Since velocity is related to flow rate based on the area, what we can do is we can say that the flow rate squared divided by the area will give us the flow rate times the velocity. So so there's for section 1. Here's for section 2. And so basically what we can do is we can say, this thing right here, let's call that specific force. And so that's how we're going to solve these kind of problems. So most of the time we won't have an object in the flow path, so we can kind of just say, hey, m1 is equal to m2 for these hydraulic jumps. So we're going to use that a lot. The next thing we need to talk about is water surface profiles. So for this section, we need to use the Froude number to understand the control direction. So this is a tricky thing to figure out. Basically, we want to keep in mind that water that's moving slower than the speed of a wave will be controlled by downstream conditions. And so let's just take a look at this and see if we can kind of come to grips with it. So some of the kind of points of references that we'll use is we'll consider normal depth as a kind of point of reference. And so the idea is that if the current channel conditions lasted for a really long time, what would the depth and velocity and other properties of the channel be? And then if it's not that, then we can try and solve the problem to come up with whatever it is that we're looking for. If there's going to be a discrete step or constriction or some kind of thing that is not gradually varied flow, then we'll use either the energy or the momentum ideas to move across that section from upstream or downstream to the direction that we're trying to go. And so, so these things are going to be grouped based on the slope of the channel. And we haven't talked about that. It's not even the slope of the channel. It's the normal depth is the Froude number less than 1 or greater than 1. So the idea we need to figure this out is that a mild channel or a mild slope for a given flow rate is going to say basically that the normal depth and the Froude number associated with the normal depth are subcritical. And so what that means is that most of the time downstream controls, but the thing is that we want to take into consideration all the possibilities. And so let's just look at this first section. So this is the idea of what possible water surface profiles we could have for a mild slope. And so what we would do first is determine normal depth, and then we would be able to figure out, is this a mild channel or not, or mild slope? And so it is in this case. And so what we can see is like the first curve is a backwater curve. So that's called an M1 curve. So that'd be flooding from downstream conditions. The next curve is an M2 curve, and that's actually where water, as it's moving downhill, is going to accelerate over something. So maybe it's a change in slope, maybe it's a section enlargement, but it's accelerating, and what that means is that it's going to be getting shallower. And then lastly, what if the water is moving supercritical already? So for example, if we put a sluice gate in, and water's got to rush under that thing, it's going to take off. It's going to go really fast. In fact, it's going to be faster than the speed of a wave. And so even though this is an M3 curve, and what's happening is it's actually burning off a ton of energy as it's moving so fast. So what it does is it slows down. It gets shallower, it gets deeper, and eventually it will jump. So there will be a hydraulic jump that connects to the other side. So we're going to group these together. We're going to label them M1, M2, or M3, and we'll decide based on the normal depth slope. So same thing for steep. So this is steep. It's just a little bit backwards. So here in this case, we've got normal depth coming in, but there's some flooding condition. And so all of this section right here, this is all subcritical. The water's moving slower than the speed of a wave. But that water surface profile is defined by the slope being steep. So again, we would go to the normal depth and we would figure out, what's the Froude number? Is it supercritical or is it subcritical? So any kind of flooding could cause an S1 curve. You just need a steep slope. You could also get a case where water's sort of like accelerating over a change in slope. Maybe it's a steep slope and it's going to be even steeper, or in this case, they're showing a section enlargement. So what you get is water's still maybe moving supercritical, but then after this change in slope, it accelerates, and so that curve is going to be called an S2 curve. And then finally, sometimes we'll have the water decelerate. So if we had a really steep slope followed by another steep slope, which is not as steep, the water would be moving a lot faster than it would at normal depth, so it's going to burn off more energy than it gains, and so that thing, as it moves downstream, is going to approach normal depth. So that's an S3 curve. So to try and draw this, it's tricky. We need to have a scenario, and the first scenario is a M1 curve, and that's just a type of flooding curve. And so to be able to make these things go, we need to be able to identify on the screen what critical depth is. And we're going to solve, there's a way that you can solve for that directly, but we're going to solve for it. And then we also need to be able to identify what normal depth is. So that's going to be, I'm going to try and use red and green for those. And then, so let's say that, so normal depth is greater than critical. So this is a mild slope. And let's just say we got something going on downstream. There's a lake or there's a dam or a bridge or something like that, and it's causing the water surface to be right here. So we know this point and we want to go upstream, and we want to know what the depth is upstream. So in this case, it's downstream control. So our control direction is going to move upstream, and we're going to actually be able to calculate these steps. But the first thing to do is to sketch out schematically like that we understand what's going on. So the water surface profile is going to approach normal depth asymptotically as it moves upstream. How about in M2? So again, critical depth. And normal depth. So normal depth is greater than critical depth. That makes this a mild slope. So let's say that this slope actually gets steeper. Well, let's just say there's a waterfall. And so this water is going to sort of race off this. And what it's going to end up doing is it's actually going to go over the waterfall right at critical, just a little bit before the edge of the waterfall. It goes through critical. And so we know this point now. And we also know that the water normally wants to be subcritical. So that means downstream controls. So we're going to move our way upstream. And we can do these calculations directly, but first we want to kind of get a sense of it. So this is going to be an M2 curve. The M3 curve is, there's a lot of different scenarios for each of these, but the M3 curve that I'm going to present here is a steep slope followed by a mild slope. And so if we put critical depth on there, that just has to do with the surface wave speed and comparing that with the velocity in the channel, so that it turns out that doesn't change with the slope. Normal depth does. So in the steep section, normal depth is shallower than the critical depth. And in the mild section, normal depth is deeper than the critical slope. And I'll show you how to calculate these, so don't sweat that part yet. So in this case, the water is moving down, and it hits this point and is going to burn off that energy quickly until it gets to a point where it can hydraulic jump, and it will go straight to uniform depth. There's another scenario, and it's probably not a bad idea to talk about it now. So the other scenario would be potentially that this water surface profile extends up, and we've got an S1 curve to a hydraulic jump. So this could be an S1 here, or we could have an M3. But at the end of the day, we're not ready to solve that problem yet, but we'll approach that pretty soon. And the way we're going to do that is we're going to look at this point as a dividing line, and we'll say, well, what would happen if the hydraulic jump was right there? Would it be pushed upstream or would it be pushed downstream? And that's how we're going to solve that problem. So for steep slopes, the S1 curve is a backwater curve. So we've got a steep slope. Normally the water wants to be at that depth. This is the depth for critical. So the speed, if the depth was that deep, the velocity would be the same as the speed of a wave. And we've got an obstruction downstream. It's a bridge or a culvert or something like that. And so what we end up with is this S1 curve, and it will, so it's subcritical, right? And I skipped, I'm going to go back to this M3 curve. We got to this point, and then we actually continued to work our way downstream. here we're going to work our way back upstream. Even though this is a steep slope, the water is moving subcritically. So we're going to go downstream to upstream. It's going to burn off. And it will actually be a uniform depth jump to the S1 curve. Oops. So what if we have an S2 curve? How could we get that? So the S2 curve I'm going to draw as a mild slope followed by a steeper slope. And so again, if we draw critical in here, it's the same on both sides. But normal depth is not. And so what will happen is it's going to go through critical right here. And so that's our control point, and we're going to be able to have an S2, sorry, that's an M2, followed by an S2 curve. And then lastly, the S3 curve is like a really steep slope going into another steep slope. Oops. And so critical depth is going to be the same on both the slopes. So the normal depth in the steeper section is shallower because the water can move faster. So in this case, we're going to start upstream and we're going to say, hey, you know, if we go far enough upstream, it's going to be normal depth. And so we'll keep moving downstream until we get something that changes. And that thing that changes is the slopes. Now this is the point that we know. And it's going to asymptotically approach normal depth as it goes downstream. So this is an S3. So I guess the takeaway might ought to be that if we look at these sections, whether they're mild or they're steep, we can break those sections down like this. So depending on if it's mild or if it's steep, this could be normal depth or it could be critical depth, right? It could be either one of those, and those are going to switch based on whether it's steep or mild. All the time that you see a steep slope, normal depth is going to be less than critical depth. And so conversely, for a mild slope, it's always going to be normal depth is going to be deeper than critical. So basically, you'll identify the slope type, M or S, and then you'll figure out where the curve is actually going to land. Is it 1, 2, or 3? And that's how we'll describe these things. Rapidly varied flow is another thing that we'll be trying to do. So the idea is that you know, maybe we've got water going down a hill, and then we've got this S3 curve and then a hydraulic jump. And so we want to know, hey, what's the depth here and what's the depth there? And so for that, we'll use the momentum equation. Also, you know, if we had a sluice gate, so that's just a gate that impounds water. What happens is the water accelerates underneath that gate. And what we can say is that the Bernoulli sum here at section A is equal to the Bernoulli sum at section B, or the specific energies are the same. And so we can get from A to B using energy, or even for a waterfall. So that's it. We're not going to go through anything else. What we need to do now is we need to actually do a bunch of examples to try and get used to all of these topics and being able to use them. So to be able to do that, to do the examples effectively, we need to go through and set up that spreadsheet. So I'm going to show you the spreadsheet next.